Okay. All right, let's look at this scenario. And I've put this and its solution on Schoology. If you want to take notes, great. And if you get behind, then, and I'm also going to put, in essence, this video on Schoology as well. But let's look at this scenario and see if we can figure out these problems. So Monique runs a pet spa that has several thousand customers. Last year, 80% of her customers reported being happy with the service at the spa. She decides that if she has statistically significant evidence that less than 80% of her customers are happy with the service this year, she will change the way she runs the spa. She takes a simple random sample of 500 of her customers and performs a test of significance at the significance level of alpha is 0.03. Okay, so what that means is if she gets a p-value below 0.03, she's going to reject the null hypothesis. Okay, if it's above 0.03, then she's going to fail to reject the null hypothesis. All right, so number one, and this is a comment, we've had this many times. I just want to make sure because it's on the exam every year. What is the significance of there being several thousand customers? Well, one of the conditions is the fact that your sample size can't be more than 10% of your population size. So when you look at this, you look at your sample size and you say, well, there's 500 in the sample. There's got to be at least 5,000. There's got to be at least 5,000 total. Otherwise, independence won't be met and you won't be able to use the formula for the standard error. So it says there's several thousand. And so you would say, all right, so the significance of that is the population size, which is big N, must be at least 10 times the sample size, which is little n, or, the other way of saying it is the sample size can't be more than 10% of the population. And so this means we can use the formula for standard error. Okay, it's a commonly asked question. A lot of people miss it just because they don't know that fact. So make sure to know that fact, okay? Number two, another big fact that you have to know is what ensures normality in our sampling distribution. So let's see here. Let me let these people in. And all right, remember, and it's been this way for the past 3 chapters now, what ensures normality with a proportion, and that is n times p and n times 1 minus p have to be greater than or equal to 10. Okay, and last chapter we used p hat. Well, here we're actually not given a p hat. So we use p naught, which is this 80%, which is the claimed value or the status quo, the null hypothesis value. And so our sample size is 500. So this would be 500 times 0.8, and then 500 times 0.2. And so that would be 400, and that would be 100. They're both greater than or equal to 10. So thus normality is met. So, okay, we've had that several times. Just want to make sure you know it, okay, because it will be asked of you. There, you're going to get 2 questions right. Great. All right, now here's a harder problem. And that is this. And this is, it's on the exam from time to time. And that is this. What values of the sample portion would cause you to reject the null hypothesis? All right, so first of all, what are our hypotheses? That's new in this chapter. All right, so you have the null hypothesis, which is always going to look like this. H sub O P is equal to some number, okay? That's what it's going to look like in this chapter, okay? And actually in section 3, it's going to be that the 2 P's are equal to each other, but that's next week. All right, so in this case, the claimed value for P is 80%. That is our value that we are in essence testing. All right. The alternative is what we suspect might be true or what would call for a change or for a difference, and it's less than. That is what's going to cause the problem. If she has evidence that less than 80% of her customers are satisfied, then she's going to change things. So it would be less than, like that. And of course, if you were writing this full out, you would define, P is the proportion of our customers that are happy this year. All right. So how low? So in other words, if our value for P hat is way low, in essence, a 0.8, we are going to reject it. Well, how low does it have to be? And that gets to the concept of a sampling distribution, which we did in chapter 7. All right, if we assume that all hypothesis is true, and that's what we're doing in a hypothesis test. So 0.8, if we assume that's the true value, our sample value, our p hat, is probably going to be somewhere close to there. It'll probably be somewhere near there, our sample proportion. And if we took another sample and found another p hat and took many different samples and found many different p hats, this family of p hats is what we call a sampling distribution. It's approximately normal because of this, because n times p and n times 1 minus p are greater than 10. Okay, and so there's every possible value of p hat. So the question is, how far down here do we have to go to get a p hat? How far below 0.8 do we have to go to get to the point where we're saying we're rejecting the null hypothesis? Because this is so far out, it's unlikely to occur by sampling variability. I mean, if we get a p hat in here, you know, like if we get like 0.79 something, you know, we would be like, well, it's less than 0.8, but it's not statistically significantly less. So how do we find this value? That is what alpha determines, okay? Alpha is, of course, the value is that if our p-value, our probability is less than that, we reject it, okay? And so alpha is, in essence, the percent of our curve that we're rejecting. Okay, so if alpha is 0.03, that means we're rejecting 3% of the curve. It means this area is 0.03. So alpha is, in another way of looking at alpha, it's the area we're rejecting. So anything below here, this is what is known as our rejection region. And if we get a p hat, below this value, now, how do we find this value? That is our question. Okay, and we actually did this in chapter 2. That is a function called inverse norm. Remember, normal CDF is a calculated function that tells us an area in the normal curve. But if we're given the area and had to find the x value, we use inverse norm. And so that's what we're going to do. And we use left area. Our left area here is 0.03. Our mean is 0.8. And then, of course, our standard error, or our standard deviation, which we've been doing for 3 chapters now, it's the square root of p times 1 minus p over n. Either one of these two, actually. And so that would be the square root of 0.8 times 0.2 over our sample size, which is 500. Just like that. This is our left area. So to show your work, you write left area, the mean of my p hats, the sigma of my p hats. And so let's get that. And so here we go. And so remember, normal, inverse norm is in the distribution menu right above the vars button, right? So you're just going to go second vars, which is distribution, inverse norm. There it is. And so the area is 0.03. And then the mean is 0.8. And then the standard deviation would be the square root of 0.8 times 0.2 divided by 500. Boom. So that's it, 0.76636. 0.76636. So anything below that, we would reject. Anything below 0.76636 would cause us to reject the null. That's it. That is how you find the values of p hat that you would reject using inverse norm with the left area. Yeah. Any questions about that? Let me say this to you on your test question. You'll be asked a test. Let's just pretend you don't understand that. And it asks you this very question. And it says, what values of p hat are going to cause you to reject the null? Well, because it's multiple choice, I mean, you're going to pick the most unusual one. In other words, for this one, you'd pick the one that's furthest to the left. Otherwise, because if I had 2 of them down there, then you'd have 2 correct answers. So in other words, just pick the most, on the test, you can just pick the most unusual one. So there, I told you. So you get rewarded for showing up today. All right, great. So that's that. All right, now let's look at number 4. So for number 4, it says this. All right, describe type 1 and type 2 error in the power and the context and mission the conquest. All right, whenever I'm asked about type 1 and type 2 error, this is what I do. Before I even look at the problem, I immediately write this down. 1 is hot. 1 is hot. 1 is hot. And what that means is, in type 1 error, the null hypothesis is true. And it's an error, so I must have rejected it. But I rejected it. Okay, and then type 2 error is sort of the vice versa of that. So in type 2 error, okay, that is when the null is false. The null is false. And it's an error, so I must have failed to reject it. But I failed to reject the null, reject it. And then power goes along with type 2 error. But you do the right thing. Is the null is false, the null is false. Power is the probability that I do the right thing, that I reject it. Okay, there it is. All right. So, in this situation, let's talk about type 1 and type 2 error and power. So here's our hypotheses right here. So what is type 1 error? Now, and by the way, when you read this problem, what it's saying up here, it says if she has evidence that less than 80% are happy, she's going to change the way she runs the spa. Okay. So in other words, if in fact the alternative is true, if P is less than 0.8, she's going to change her spa. Okay, in essence. So that is what in essence our things are. So type 1 error. So when we're asked to describe type 1 error, so in type 1 error, you say, well, the null is true. In other words, okay, type 1 error means P really is equal to 0.8, but I say that it's not. I say P is less than 0.8. Now, what does that mean in context? That means that Monique does the changes. She changes her spa, but she shouldn't have. She shouldn't have. Okay. In other words, she thought the portion of the people happy was less than 0.8, but it was actually equal to 0.8. And actually things were going good. So that's type 1 error and the consequences of it. Okay. Type 2 error. So I immediately look at this. Well, type 2 error means the null is false. So I say, well, okay, so the null really is false. In other words, P really is less than 0.8, but I say the opposite of that, which is P is equal to 0.8. I say that the null is I say the null is true. Okay. So what does that mean? It means she should be making changes, but she doesn't. Okay. Monique does not make changes, but she should. Yeah. Okay. All right. And so what is power? All right. So power is this, and power is the probability. Okay. Power is a probability. It is the probability. It is the probability that the null is false. Okay. So the null is false, and the probability that P is less than 0.8. In other words, she should make changes. She should make changes. And I say that she should make changes. Okay. And that can, these can be, these can be sort of confusing problems, but anyway. So, all right, so the last thing I want to say about that, aside from any questions you have, remember, all right, this can be a bit complicated. What's not complicated is this. You're not going to miss this question. It'll give you some complicated scenario, and then it's going to ask, what's the probability of type 1 error? The probability, and it's the easiest question in the world. It is always equal to whatever your alpha is. So it's 0.03 in this problem. Okay, please don't miss that problem. That's an easy, probably type 1 error is always equal to alpha. Okay, and then always remember the probability of type 2 error is always equal to 1 minus the power. Okay, so that's been on the exam a lot. Okay, and people miss it because they don't know that fact. So if you ask the probability of type 2 error, it's just 1 minus the power. If it says the power is 0.56, you just say 1 minus that's 0.44. There you go. You got it right. And so, and then that means you could change this equation. Power is equal to 1 minus probability of type 2 error. So it didn't ask that here, but it will on your test. So get that right. Okay, that's an easy thing if you know what you're looking for. Okay, so so that is that. And just a couple other things I wanted to chat about. All right, so this one. All right, let's think about this one. All right, so if Monique decides to do a two-sided test instead of a one-sided test, what values of the sample statistic would cause her to reject a null? Okay, so two-sided test means this. She's not just testing for less than 0.8. She's also testing for greater than 0.8. In other words, she's testing for not just lower than 0.8, but also greater than 0.8. So our null on a two-sided test, of course, the null hypothesis would be the same. So this is number 5. The null hypothesis is just P is equal to 0.8. On a two-sided test, this is what's happening. So P is not equal to 0.8. Okay, not equal to 0.8. And so what's happening there is this, is if we're asked to find, okay, what values of P hat would cause you to reject 0.8? All right, so here's our sampling distribution. It's centered at 0.8, and every point in this curve is a P hat. So what values of P hat would cause me to reject the null? Values that are not only way down there, but also values that are way up here. Well, what determines these values? How high do we have to go? And that's alpha. In this case, alpha is equal to 0.03. Now, and so we did this before, but now it's a two-sided test. And so we're rejecting everything that's up here that's too big and everything that's too low. Everything that's too low. Alpha is the total area of our rejection region. Okay, so 97% is inside. That means 3%, okay, 3% is outside. And these two tails, they're perfectly symmetrical. So each tail has to contain 1.5%. So there's got to be 0.015 there and 0.015 there. So when you have a two-sided test, you're splitting up your alpha like that. Well, how can we find this X value and this X value? Inverse norm. So we will say inverse norm of 0.015 and then the same mean and standard deviation, square root of 0.8 times 0.2 over 500, right? Yes. Okay, so let's see what that is. So we would say second distribution, inverse norm, 0.015, same mean, same standard deviation. And so we get that 0.76118. So that one, so anything less than 0.76118. Now, what about here? All right, well, let's think about that. So now on my calculator, you could actually do the right area, but I like doing the left area because some calculators don't have that option. So what's the percentile here? In other words, what's all of this added up? Okay, well, there's 97% in here, since there's 3% on the outside. So the total area to the left is going to be 98.5%. So for this one, it's going to be inverse norm of 0.985, mean of 0.8, standard deviation, square root of 0.8 times 0.2 over 500. So, and so let's see what that is. And so we go second distribution, inverse norm, 0.985. And so that would be anything greater than 0.83882. Yeah, that's, you know, there you go. On your test, once again, if something like this happened, you would just pick the multiple choice options that are the furthest to the outside. Because if I didn't do that, then I would have 2 potential correct answers, and there isn't that. So, and so that is that. Okay. And And the last thing that I wanted to remind you of, as far as sort of tough problems, is when you're asked to find, okay, so when you're asked to find a, when you're asked to find a p-value given your test statistic, okay? For instance, so like, let's just say this. Let's say if we had the null hypothesis is p is equal to 0.8, and that's the null, and let's say that the alternative, going back to what it was originally, so p is, let's say, less than 0.8, okay? Let's just pretend you're given a test stat equal to, let's say negative 1.6, okay? In other words, you get a sample value that is 1.6, and this is z. Your test stat z is equal to 1.6. Let's just pretend you're given that test stat. How do you find a p-value? Well, that's with normal CDF. And so what you would do is you would say normal CDF, and since this is less than, you're going from that to infinity. So it'd be from negative infinity to negative 1.6. If this was greater than, you'd go negative 1.6 to infinity, and it's mean of 0, standard deviation of 1. So when you're given your z test stat, that's the way you find a p-value. And so your p-value would be normal CDF, negative infinity to negative 1.6, mean of 0, standard deviation of 1. And so that would be your p-value. So that would be just above your alpha, so you would not reject your null. And so, okay, that's